Hello, and welcome to Sleep Archive. Tonight, we leave the frantic pace of the human world behind and step into the silent, cathedral-like atmosphere of the ancient forest. We will undertake a journey that spans hundreds of millions of years, tracing the slow, green rise of life from the primordial waters to the towering canopy of the giants. We will explore the complex chemistry of photosynthesis, the hidden fungal networks that bind the roots together, and the stoic endurance of wood that allows a tree to stand for millennia. As we settle into the rhythm of the leaves, we begin our exploration not with the trees themselves, but with the distant, watery past from which they emerged. To understand the forest, we must first cast our minds back nearly 500 million years to a time when the continents of Earth were barren, rocky, and silent. In this ancient epoch, the land was a harsh and desolate place, scoured by wind and burned by ultraviolet radiation, utterly devoid of the green softness we know today. Life was almost entirely confined to the oceans, where vast mats of algae floated in the sunlit currents, bathed in a nutrient-rich soup that provided everything they needed to survive. For these aquatic ancestors, life was structurally simple. Supported by the buoyancy of the water, they had no need for strong stems, deep roots, or protective skins. But life has a persistent tendency to expand, and slowly, the green edges of the ocean began to creep up onto the damp, rocky shorelines. This transition from the water to the land was the single greatest challenge in the history of the plant kingdom, a feat of biological engineering that required a total reinvention of the organism. The first pioneers to make this journey were the bryophytes, the ancestors of the mosses and liverworts we still see clinging to damp stones today. These early plants were small and humble, hugging the ground tightly because they lacked the internal plumbing to transport water upward against gravity. They were essentially amphibious, unable to survive far from moisture, soaking up the rain and the dew directly through their cells like a living sponge. However, the land presented a new and deadly enemy that did not exist in the ocean: desiccation, the constant threat of drying out in the open air. To survive this, plants had to invent a way to seal themselves off from the atmosphere while still allowing light to enter. The solution was the cuticle, a thin, waxy layer that coats the surface of the plant, acting as a waterproof seal that keeps the precious internal fluids from evaporating. But this waxy shield created a paradox. While it kept the water in, it also kept the essential gases, like carbon dioxide, out. The plant was effectively holding its breath to keep from drying out. The evolutionary answer to this problem was the development of stomata, microscopic, mouth-like valves on the surface of the green tissue. These tiny pores could open to let the air in when moisture was abundant and snap shut tight when the air became dry, giving the plant control over its own internal atmosphere for the first time. With the cuticle and the stomata in place, the green conquest of the land could truly begin. Yet, these early forests were low and flat, a carpet of green that rose only a few centimeters above the mud. To reach the sunlight and to scatter their spores further, plants needed to solve the problem of gravity, they needed to stand up. This required the development of a structural support system, a way to stiffen the cell walls against the pull of the earth. The first steps toward height were tentative, producing plants with simple, forking stems that looked more like alien candelabras than trees. But the evolutionary pressure was relentless. The taller you grew, the more sunlight you could capture, and the more you could shade out your competitors below. This race for the light set the stage for the next great leap in biological architecture, the invention of wood and the rise of the vascular system. We are standing at the dawn of the vertical world, where the flat green carpet is about to erupt into a three-dimensional forest. The water has been left behind, the skin has been toughened, and the first breath has been taken. We rest in the humidity of this primeval landscape, watching the slow, determined march of the mosses as they prepare the soil for the giants to come. The transition from these soft, low-lying pioneers to the towering structures of the future is a move from existence to architecture. The journey continues toward the invention of wood, where we will witness the chemical revolution that allowed life to lift itself into the sky. We acknowledge the watery origins as the humble beginning, the wet roots of a family tree that will eventually cover the continents. As the competition for sunlight intensified on the early continents, plants faced a physical barrier that seemed insurmountable, the tyranny of gravity. To grow taller than a few centimeters, a plant needed more than just water pressure to hold itself up. It needed a skeleton, a rigid material that could support the immense weight of a vertical column against the downward pull of the earth. Evolution's answer to this engineering problem was the synthesis of a revolutionary new material, a biological composite that would change the face of the planet forever: wood. The architecture of wood is based on a partnership between two distinct chemical molecules, each providing a specific physical property. The first is cellulose, a long, chain-like molecule made of sugar that had been used by algae for millions of years. Cellulose possesses incredible tensile strength, meaning it is very hard to pull apart, but it is flexible and floppy, like a cotton rope. You can build a mat out of cellulose, but you cannot build a tower. Under its own weight, it simply buckles and folds. To solve this, plants developed a second, far more complex molecule called lignin. Lignin is a chaotic three-dimensional polymer that acts as a hardening agent, a biological cement that fills the spaces between the cellulose fibers. When these two are combined, the tensile strength of the cellulose fibers embedded in the rigid matrix of the lignin, they create a natural composite material that is stronger, pound for pound, than steel. This is the same principle used in modern reinforced concrete. The cellulose acts as the steel rebar, providing flexibility and tension, while the lignin acts as the concrete, providing stiffness and compression strength. With this invention, the plant cell walls hardened from soft, pliable membranes into rigid, structural boxes. This allowed plants to stack their cells on top of one another, millions high, building self-supporting towers that could lift their photosynthetic leaves hundreds of feet into the air. The arrival of wood triggered the Carboniferous period, an era of explosive growth where giant club mosses and primitive ferns formed the first true forests, shading the earth in a way that had never happened before. However, this new material was so tough and chemically complex that, for millions of years, nothing on Earth could actually decompose it. Bacteria and fungi had not yet evolved the enzymes necessary to break down the lignin bond, so when these ancient trees fell, they did not rot. Instead, they piled up in vast, non-decaying heaps, layer upon layer, eventually being compressed by geological time into the massive coal deposits that power our world today. The invention of wood was not just a biological trick. It was a planetary event that locked away billions of tons of carbon and flooded the atmosphere with oxygen. It turned the forest into a fortress, a structure capable of withstanding the wind, the rain, and the pull of gravity for centuries. This rigid architecture provided the stable framework necessary for the development of complex internal plumbing, the pipes and vessels that would eventually carry water to the sky. We rest in the strength of this material, feeling the solidity of the trunk and the hardness of the branch, acknowledging the chemical genius that allows a living thing to turn sugar into stone. The transition from the structural skeleton to the energy that builds it is a move from the hardware to the power source. The journey continues toward the green foundry, where we will enter the leaf to witness the capture of the sun. We acknowledge wood as the backbone of the forest, the enduring invention that allowed life to conquer the vertical world. We have explored the structural skeleton of the tree, the rigid wood that holds it against the sky. But to build this skeleton, the forest requires a source of energy, a way to forge solid matter out of the intangible raw materials of the universe. This miracle occurs in the leaf, the green foundry of the plant, where the most important chemical reaction on Earth takes place, photosynthesis. At its core, photosynthesis is the act of turning light into matter, of catching the fleeting, weightless energy of a photon and locking it into a solid chemical bond. If we were to zoom into the surface of a single leaf, passing through the waxy cuticle and the open stomata, we would find ourselves inside the mesophyll cells, packed with millions of tiny, disc-shaped organelles called chloroplasts. These are the engines of the forest, the biological machines that drive the entire biosphere. Inside each chloroplast are stacks of membrane coins called thylakoids, filled with a pigment known as chlorophyll. Chlorophyll is a magnesium-based molecule that acts as a quantum antenna, tuned specifically to the frequencies of red and blue light. When a photon from the sun, having traveled 93 million miles through the vacuum of space, strikes a chlorophyll molecule, its energy is instantly absorbed, exciting an electron into a higher state. In a fraction of a second, the plant uses this stolen solar energy to perform an act of chemical violence. It splits a water molecule apart. This splitting of water, H2O, releases electrons to power the cell, protons to drive the engine, and a waste product that the plant does not need, oxygen. This waste is the very breath of our existence, a byproduct of the forest's thirst for hydrogen that has oxygenated our atmosphere for billions of years. But the process does not end there. The energy captured from the light is then sent to a second stage, a silent, dark cycle of construction known as the Calvin cycle. Here, in the fluid stroma of the chloroplast, the plant takes carbon dioxide gas from the air and uses the solar energy to weld the carbon atoms together, one by one. It is a process of knitting, stitching the invisible gas into chains of solid glucose sugar. This sugar is the universal fuel of life, the concentrated energy of the sun stored in a stable, edible form. But most importantly, this sugar is the raw material for cellulose. The plant takes the sweet energy it has made and spins it into the tough, structural fibers of wood. This leads us to a profound realization that defies our intuition. A tree does not grow primarily from the ground. When you look at a massive sequoia weighing 2 million pounds, nearly all of that mass, the trunk, the bark, the branches, was pulled out of thin air. The soil provides trace minerals and water, but the solid body of the tree is made of processed atmosphere, forged by the energy of the light. A forest is essentially air that has been woven into a solid shape by the power of the sun. We rest in the presence of this quiet industry, listening to the wind in the leaves, knowing that in every single cell, the sun is being captured and the air is being turned into wood. The transition from the creation of sugar to the movement of these resources is a move from production to logistics. The journey continues toward the physics of ascent, where we will solve the impossible hydraulic puzzle of lifting water to the clouds. We acknowledge the leaf as the master builder, the green solar panel that feeds the world. We have built the wood and we have captured the sun, but we are now faced with a problem of pure physics that should, by all rights, be impossible. In a giant redwood or a towering Douglas fir, the leaves can be suspended nearly 300 feet above the ground. These leaves are thirsty engines, requiring hundreds of gallons of water every single day to perform photosynthesis and keep their cells cool. Yet, unlike animals, trees have no heart to pump fluids, no moving muscles to squeeze the veins, and they are fighting against a gravitational force that limits a mechanical suction pump to a height of only 33 feet. So, how does a tree lift thousands of pounds of water 30 stories into the air in total silence without moving a single muscle? The answer lies in the unique properties of water itself and a system of microscopic plumbing known as the xylem. The xylem is the wood's internal pipeline, a network of dead, hollow cells stacked end to end to form continuous, microscopic tubes running from the deepest root tips to the highest veins in the leaf. But the tree does not push the water up these tubes. Instead, it pulls it. The engine of this ascent is the sun. As sunlight strikes the leaves high in the canopy, it causes water to evaporate from the moist internal cells and exit through the open stomata into the dry air. This process, called transpiration, creates a tiny void, a negative pressure or tension at the very top of the water column. Because water molecules are chemically sticky, held together by hydrogen bonds in a phenomenon called cohesion, they act like a continuous, solid rope rather than a liquid. When one molecule evaporates from the leaf, it physically pulls the molecule behind it to take its place. That molecule pulls the one behind it, and so on, creating a chain reaction of tension that extends all the way down the trunk, through the roots, and into the soil. The entire tree is essentially drinking through a straw 300 feet long, powered entirely by the evaporation at the top. This transpiration stream is under immense tension. If you were to listen to the trunk of a thirsty tree with a sensitive enough microphone, you would hear the ultrasonic clicks of the water column snapping under the strain, a phenomenon known as cavitation. While the xylem carries the water up, a second system, the phloem, carries the sugar down. The phloem consists of living tissue located just beneath the bark, transporting the sweet, thick sap created in the leaves down to feed the hungry roots and the growing trunk. This two-way traffic creates a silent vertical river inside the wood, a fast-moving stream of water rising in the center, and a slow, syrupy flow of sugar descending on the outside. The physics of ascent is a masterpiece of hydraulic engineering, utilizing the polarity of water and the heat of the sun to defy gravity on a massive scale. As you visualize this, imagine the sheer tension held within the trunk of a giant tree, a silent, taut cable of water stretching from the earth to the sky. We rest in the awe of this mechanism, understanding that the forest is not static, but is vibrantly alive with the rush of fluids, a hidden torrent moving silently behind the bark. The transition from the vertical transport to the source of the water is a move from the pipe to the pump. The journey continues toward the underground city, where we will enter the dark, complex world of the soil. We acknowledge the xylem as the lifeline, the fragile thread of water that connects the darkness of the soil to the light of the sun. We now leave the sunlit world of the canopy and the vertical highways of the trunk to descend into the dark, dense foundation of the forest. Beneath the layer of fallen leaves and moss lies the underground city, a complex, sprawling metropolis of roots that is often just as massive and intricate as the tree we see above. There is an ancient saying in forestry, "As above, so below." For every branch reaching for the light, there is a root delving into the dark, anchoring the giant against the wind and searching for the water that fuels the ascent. The architecture of a root system is not a random tangle, but a strategic, intelligent search pattern. At the very end of every growing root is the root tip, a sensitive, navigating organ protected by a hard, slimy helmet called the root cap. Charles Darwin himself hypothesized that the root tip acts like the brain of the plant, sensing gravity, moisture, and obstacles, and steering the growing tissue around rocks to find the path of least resistance. But the heavy woody roots are merely the highways. The real work is done by the root hairs. These are microscopic, delicate filaments that grow by the billions from the surface of the younger roots, vastly increasing the surface area of the system. If you were to take the root hairs of a single mature rye plant and lay them end to end, they would stretch for over 6,000 miles, enough to span the Atlantic Ocean. This immense surface area is necessary because the soil is not just dirt. It is a stubborn chemical vault that locks its nutrients away tight. Minerals like calcium, magnesium, and potassium stick to the surface of clay particles like magnets, held there by strong electrical charges. To get them off, the tree must engage in a process of chemical mining known as cation exchange. The roots pump positively charged hydrogen ions, essentially mild acid, out into the soil water. These hydrogen protons swarm the clay particles and physically knock the mineral nutrients loose, taking their place on the clay surface and freeing the minerals to be absorbed by the root. It is a transaction of pure chemistry. The tree trades a proton for a nutrient, dissolving the rock of the earth to build its living tissue. This underground world is a place of high pressure, total darkness, and fierce competition for space. Yet, the roots do not work alone. They have realized that their reach, no matter how vast, is limited by the thickness of their own bodies. To access the finest pores of the soil, the tree needs a partner, an entity that lives entirely in the microscopic realm. We rest in the damp, cool earth, surrounded by the silent, powerful expansion of the root mass, feeling the tree gripping the planet with millions of tiny fingers. The transition from the root to the partner is a move from independence to symbiosis. The journey continues toward the fungal bridge, where we will discover the wood wide web. We acknowledge the root system as the anchor and the miner, the hidden half of the forest that makes the visible half possible. As impressive as the root system is, it faces a physical limitation. Even the finest root hair is too thick to enter the microscopic pores of the soil where the most valuable water and nutrients are hidden. To solve this, the forest has negotiated the oldest and most successful trade agreement on Earth, a symbiotic partnership known as mycorrhiza, meaning fungus root. If you were to gently peel back the leaf litter on the forest floor, you would see a vast, cobweb-like network of white threads running through the soil. This is not the root of the tree, but the mycelium of a fungus, a sprawling, subterranean organism that lives in intimate contact with the plant. The threads of the mycelium, called hyphae, are unimaginably fine, 100 times thinner than a root hair, allowing them to navigate the labyrinth of the soil with ease. They act as an extension of the tree's own root system, massively increasing the volume of soil the tree can exploit. The terms of the partnership are simple and strict. The fungus is a master miner, dissolving rock to extract phosphorus and nitrogen, and sponge up water, which it delivers directly into the tree's roots. In return, the tree, living high in the sun, pumps liquid sugar down into the roots to feed the fungus, which lives in the dark and cannot photosynthesize. Up to 40% of the sugar a tree produces is paid as a tax to its fungal partners, a massive investment that proves just how essential this relationship is. But this network does more than just trade. It connects. Scientists have discovered that the fungal threads do not just connect to one tree, they link root system to root system, binding the entire forest into a single, interconnected web, often called the wood wide web. Through these fungal pipelines, trees can actually share resources with one another. A massive, ancient mother tree, basking in the full sun of the canopy, can shunt excess carbon and nutrients through the network to support the shaded seedlings growing in the understory. Without this subsidy from their elders, many of these young trees would starve in the gloom of the forest floor. The network even allows for cross-species altruism. In some seasons, a birch tree with no leaves will receive carbon from a fir tree that is still green, and later the favor will be returned. This discovery shatters the old view of the forest as a collection of isolated individuals competing for survival. Instead, we see a cooperative superorganism, a socialist community where the strong support the weak, bound together by a fungal internet that pulses with chemical information beneath our feet. We rest in the knowledge of this connection, feeling the invisible threads that stitch the forest floor into a unified whole. The transition from the sharing of resources to the defense of those resources is a move from cooperation to warfare. The journey continues toward the chemical arsenal, where we will see how the forest protects itself from those who wish to eat it. We acknowledge the fungus as the bridge, the silent broker that unites the canopy with the soil and the tree with its neighbor. We tend to view the forest as a peaceful, passive place, a sanctuary of green quietude. But in reality, every tree is engaged in a constant, silent war for survival against an army of insects, bacteria, and grazing animals that view the forest as nothing more than a buffet. Unlike animals, a tree is a sessile organism, It cannot run, it cannot hide, and it cannot fight back with claws or teeth. To survive in a world of mobile predators, the plant kingdom has had to become the greatest chemical engineer on the planet. The primary defense of any tree is physical. The bark, a thick, corky armor filled with lignin and suberin that acts as a fortress wall against invasion. But when that wall is breached by the chewing mandibles of a caterpillar or the teeth of a deer, the tree deploys its second line of defense, the chemical arsenal. Inside the cells of every leaf and stem is a vast library of compounds known as secondary metabolites. These are complex molecules that are not necessary for the plant's basic growth but are synthesized strictly for warfare. One of the most common weapons is the class of chemicals known as tannins, found in high concentrations in oak trees and hemlocks. When an herbivore eats a leaf rich in tannins, the chemicals bind to the proteins in the animal's saliva and digestive enzymes, locking them up and making the food nearly impossible to digest. The leaf tastes bitter and astringent, like oversteeped tea, and the animal, feeling sick and unable to extract nutrients, learns to leave that tree alone. Other trees escalate the war further, producing deadly toxins like cyanide or neurotoxins. The yew tree, for example, produces a compound called taxine, a potent cardiac poison that can stop the heart of a horse in minutes, ensuring that very few animals dare to graze on its needles. Some plants have even evolved to weaponize their physical structure, turning their hairs into hypodermic needles. The stinging nettle, though a small plant often found on the forest floor, possesses hollow, silica-tipped hairs that break off upon contact, injecting a painful cocktail of histamine and formic acid directly into the skin of the aggressor. This is an evolutionary arms race that has been running for 400 million years. As the plants develop new poisons, the insects evolve new enzymes to detoxify them, forcing the plants to invent yet another chemical weapon. It is a slow-motion battle of biochemistry where the balance of power shifts over millennia rather than minutes. The air of the forest is thick with these invisible compounds, a silent testament to the fact that the green world is not defenseless. It is a fortress built of sugar but defended by poison, a delicate balance where beauty often masks a deadly capability. We rest in the safety of our size, knowing that these defenses are designed for the small and the hungry, not for the observer. The transition from chemical defense to chemical language is a move from repelling to informing. The journey continues toward the chemical whisper, where we will learn that trees can actually talk to one another. We acknowledge the chemical arsenal as the shield, the bitter taste that allows the slow life of the tree to endure in a hungry world. We have seen how trees defend themselves individually, but the most startling discovery of modern botany is that they do not fight alone. The forest is filled with conversation, but it is not spoken in words or carried by sound waves. It is a language of scent, spoken in the complex alphabet of chemistry. This phenomenon relies on volatile organic compounds, or VOCs, lightweight chemical molecules that evaporate easily into the air, carrying information on the wind. When a tree is attacked, say, by a swarm of caterpillars chewing on its leaves, it does not suffer in silence. Within minutes of the first bite, the injured plant begins to synthesize a specific distress signal, a plume of gas that drifts downwind to its neighbors. The neighboring trees, even though they have not yet been touched by a single insect, detect this chemical warning through the pores of their stomata. Decoding the message, they immediately ramp up their own internal defenses, pumping toxic tannins and bitter alkaloids into their leaves in preparation for the attack that is coming. By the time the caterpillars move to the next tree, they find the leaves unpalatable and tough, the forest having effectively closed its doors against them. One of the most famous examples of this occurs on the savannas of Africa, involving the acacia tree and the giraffe. When a giraffe starts eating an acacia, the tree releases a burst of ethylene gas. Acacias downwind detect this gas and instantly flood their leaves with tannins, forcing the giraffe to walk upwind to find a tree that hasn't heard the news yet. But the language of the forest goes even deeper than simple warnings. It can be a cry for help. Some plants, when attacked by a specific type of caterpillar, release a chemical signal that is not meant for other trees, but for a predator. The scent acts as a homing beacon for parasitic wasps, guiding them directly to the location of the caterpillars. The wasp arrives, lays its eggs inside the caterpillar, and effectively eliminates the threat to the tree a hired bodyguard paid for with a chemical signal. This reveals a level of sophistication that challenges our understanding of intelligence. The smell of a forest, the sharp scent of pine needles, the sweetness of balsam is not just accidental perfume. It is a complex, airborne internet of information, a constant stream of status updates, warnings, and alliances being broadcast in every direction. We walk through this invisible cloud of chatter, unaware that the silence we perceive is actually a cacophony of chemical whispers. We rest in the center of this conversation, breathing in the language of the trees, realizing that we are guests in a society that is constantly talking around us. The transition from the communication between trees to the environment they create is a move from the network to the habitat. The journey continues toward the canopy world, where we will ascend to the sunlit roof of the forest. We acknowledge the chemical whisper as the voice of the woods, the silent scream that saves the grove. We have spent much of our time in the deep foundations of the forest, exploring the roots, the soil, and the trunk. Now, we must ascend the vertical column to reach the very roof of the world, the canopy. This is the solar interface, the turbulent, bright, and windy frontier where the forest meets the atmosphere. While the forest floor is a place of shadow and stillness, the canopy is a chaotic three-dimensional desert of extreme conditions. Here, the leaves are exposed to the full, unblinking glare of the sun, the drying force of the wind, and fluctuations in temperature that can swing wildly in a matter of minutes. To survive here, the leaves of the upper canopy are often physically different from those below. They are smaller, thicker, and covered in a heavier wax to retain moisture, while the shade leaves below are broad and thin to catch the dappled light. The architecture of the canopy is defined by a ruthless competition for space. Every branch is engaged in a slow-motion wrestling match, twisting and reaching to occupy a patch of empty air where sunlight is available. However, amidst this competition, there is a phenomenon of profound respect and mystery known as crown shyness. If you were to stand on the forest floor and look up at the jigsaw puzzle of the sky, you would see that in many species, the crowns of the majestic trees never actually touch. They maintain a polite, consistent gap of a few inches between their outermost leaves and those of their neighbor, creating winding channels of blue sky that outline each individual tree. The exact biological reason for this is still debated. Some believe it is to prevent the spread of leaf-eating insects. Others think it is to avoid abrasive damage from branches colliding in the wind. Regardless of the cause, the result is a breathtaking mosaic, a visual treaty of non-aggression drawn against the light. But the canopy is not just a ceiling, it is a continent in the sky. In the ancient rainforests and the massive redwood groves, the canopy accumulates its own soil mats of decaying leaves and moss that settle in the crooks of the massive branches hundreds of feet in the air. This suspended soil supports entire ecosystems of epiphytes, plants that grow on other plants, ferns, orchids, and even other trees growing out of the branches of the giants. There are salamanders, earthworms, and insects that live their entire lives in this aerial world, born and dying in the suspended gardens without ever once touching the ground. The canopy is the engine room of the planet's climate, a massive surface area that sweats moisture into the air, creating the flying rivers of vapor that seed the rain clouds downwind. It is a world of immense biological density, a green ocean suspended in the air, teeming with life that is adapted to the high wire act of existence. We rest on a high branch, feeling the sway of the timber in the wind, looking out over the undulating green waves that stretch to the horizon. The transition from the architecture of the canopy to the future of the forest is a move from growth to renewal. The journey continues toward the reproductive drift, where we will watch the forest cast its children into the wind. We acknowledge the canopy as the crown, the chaotic, beautiful roof that shelters the world below. The forest is a place of stillness, where the giants stand rooted to the spot for centuries. But this immobility presents a fundamental biological challenge. If you cannot move, how do you find a mate, and how do you send your children out into the world? The solution is one of the most elegant engineering feats in nature, the transformation of the stationary tree into a mobile genetic traveler. This journey begins with pollen, the microscopic dust that carries the male genetic code across the void of the air. For many ancient trees, like the pines and the firs, the strategy is one of pure, overwhelming volume. They do not rely on insects or birds, they rely on the wind. In the spring, a single pine tree can release billions of pollen grains, creating vast yellow clouds that drift like smoke through the canopy, coating every surface in a fine, golden dust. This is a carpet bombing strategy, a gamble that out of a billion grains one will randomly land on the tiny, receptive female cone of another tree miles away. To aid in this flight, microscopic examination reveals that pine pollen grains are equipped with two tiny, air-filled bladders, literal wings that allow them to float on the breeze for hundreds of miles. Other trees, however, have opted for precision over volume. The flowering trees have entered into a contract with the animal kingdom, evolving bright colors and sweet nectar to bribe insects into acting as targeted couriers. Here, the pollen is sticky and heavy, designed to cling to the fuzzy legs of a bee or the feathers of a hummingbird, ensuring a direct delivery from flower to flower. Once the connection is made and fertilization occurs, the tree begins the construction of the seed, an embryonic time capsule that is built to survive the journey into the future. The engineering of seed dispersal is a masterclass in aerodynamics and physics. Consider the maple tree, which packages its seeds in a structure known as a samara, a single, perfectly balanced wing. When this seed falls, The shape of the wing interacts with the air to induce a rapid spin, creating a tiny vortex that generates lift. This helicopter effect slows the descent, allowing even a gentle breeze to carry the seed far away from the shadow of the parent tree, giving it a chance to find its own patch of sunlight. Other trees, like the oak, wrap their heavy seeds in a hard shell, the acorn, and rely on the forgetfulness of squirrels to bury them and plant the next generation. And some, like the lodgepole pine, seal their seeds inside cones that are glued shut with a heat-sensitive resin. These cones will only open to release their seeds in the presence of intense heat, waiting specifically for a forest fire to clear the competition before sowing their crop in the ash-rich soil. The reproductive drift is the only time the forest moves, a silent, slow-motion migration that allows the woods to walk across the continents over thousands of years. We watch the seeds spinning down through the shafts of light, realizing that each one contains the architectural blueprint for a giant that might live for 1,000 years. We rest in the promise of this drift, knowing that the forest is constantly engaged in the act of becoming. The transition from the tiny seed to the massive result is a move from potential to monument. The journey continues toward the sentinels of time, where we will stand at the foot of the oldest living things on Earth. We acknowledge the seed as the vessel, the tiny ark that carries the forest across the ocean of time. We have followed the journey of the forest from the microscopic cell to the drifting seed, but there are some members of this community that have transcended the normal rules of biology to become something closer to geology. We are speaking of the ancient giants, the coast redwoods, and the giant sequoias of the Pacific coast. These are the sentinels of time, living organisms that grow to such immense proportions that they create their own weather systems and support entire ecosystems within their branches. To stand at the base of a giant sequoia is to feel a profound disorientation of scale. The trunk can be 30 feet wide, a wall of bark that looks more like a cliff face than a biological stem. Some of these trees, like the General Sherman, weigh over 2 million pounds heavier than a fully loaded space shuttle, making them the largest single individual organisms on the planet. But their most impressive attribute is not their mass, but their relationship with time. Many of these giants were already saplings when the Roman Empire was at its height, and they were already ancient when the modern world began. They can live for over 3,000 years, silently witnessing the rise and fall of entire civilizations, while adding only a millimeter of width to their rings each year. The secret to this immortality lies in their defense against the two great destroyers of the forest, rot and fire. The wood of the sequoia is packed with such high concentrations of tannins that it is essentially fungicidal. It simply refuses to decay. Fallen logs can lie on the damp forest floor for centuries, remaining perfectly sound while the world around them dissolves into compost. But it is their relationship with fire that is truly unique. The bark of a mature sequoia is distinct from any other tree. It is soft, fibrous, and reddish-brown, often growing up to 2 feet thick. This bark contains almost no resin or pitch. Instead, it acts like a massive biological heat shield, an asbestos blanket that wraps the living column of the tree. When a forest fire sweeps through the grove, the flames may lick at the bark and clear away the underbrush, but they cannot penetrate to the living cambium layer beneath. In fact, These trees rely on the fire to clear the competition and heat their cones, as we saw in the previous section. They are the phoenixes of the plant kingdom, designed to endure the inferno and emerge stronger on the other side. Biologically speaking, these trees do not die of old age in the way animals do. Their cells do not have a programmed expiration date. They only die when a physical force, gravity, wind, or soil erosion finally overcomes their structural integrity and brings them crashing down. Until that day, they simply keep growing, keep photosynthesizing, and keep holding their vigil over the mountains. There is a spiritual weight to their presence, a silence that demands reverence. We rest in the shadow of these elders, touching the soft, warm bark that has weathered 3 millennia of storms. The transition from the living tree to the history written inside it is a move from the exterior to the interior. The journey continues toward the archive of rings, where we will learn to read the diary of the climate hidden within the wood. We acknowledge the giants as the sentinels, the living bridges that connect the past to the present. If we were to take a cross-section of one of these ancient sentinels, we would find more than just wood. We would find a library. Inside the trunk of every tree is a perfect, physical record of every single year it has lived, written in the concentric code of its rings. This science is known as dendrochronology, the art of reading time through timber. The architecture of a tree ring is created by the changing rhythm of the seasons. In the spring, when water is abundant and the sun is returning, the tree grows rapidly, producing large, thin-walled cells that appear light in color. This is known as early wood. As the summer progresses and the days grow hotter and drier, the growth slows down. The cells become smaller, denser, and darker, forming the hard structural boundary known as late wood. The sharp contrast between the dark late wood of one year and the light early wood of the next is what creates the visible ring, a permanent line drawn by the passing of a winter. But these rings are not just counters of age, they are detailed weather reports from the past. A wide, generous ring tells the story of a wet, lush year where the tree drank deeply and grew without restraint. A narrow, pinched ring whispers of a year of drought, a time of struggle when the tree barely managed to add a millimeter to its girth. We can see the scars of ancient fires, blackened lines where the bark was burned away, only for the tree to heal over the wound and keep growing, encapsulating the memory of the flame inside its body. We can even trace the impact of volcanic eruptions on the other side of the world. A year of summerless cold caused by volcanic ash in the atmosphere will be recorded as a frost ring, a layer of damaged cells frozen in time. By cross-referencing the rings of living trees with dead logs and the beams of ancient buildings, scientists have built a continuous calendar stretching back over 10,000 years. This archive of rings allows us to read the history of the Earth's climate long before humans invented the thermometer or the written word. The tree is an unbiased historian, dutifully recording the rain, the sun, the fire, and the cold without judgment or error. It stands in one place, absorbing the world around it, and writing a memoir that is locked away inside its heartwood, only to be revealed after its death. There is a profound intimacy in looking at the rings of a stump. You can place your finger on a specific line and say, "Here is the year the Magna Carta was signed," or "Here is the year of the Great Drought." It is a tangible timeline, a physical manifestation of memory that you can touch with your own hands. We rest in the presence of this recording, understanding that the forest is not just a collection of plants, but a living hard drive of planetary data. The transition from the recording of the past to the endurance of the cold is a move from history to survival. The journey continues toward the architecture of dormancy, where we will see how the forest sleeps through the freezing dark. We acknowledge the ring as the written word of the wood, the circle that binds the tree to the calendar of the earth. As the archive of rings records the passing of time, the forest itself must face the cyclical challenge that defines its existence, the arrival of winter. For a tree, winter is not just a cold season, it is a deadly physiological drought. When the ground freezes, the water in the soil becomes locked in solid ice, completely inaccessible to the roots. If the tree were to keep its broad, flat leaves, the dry winter winds would suck the moisture out of them, and with no way to replenish the supply from the frozen ground, the tree would die of thirst in the middle of a snowstorm. To survive this, the deciduous forest engages in a spectacular act of self-amputation known as abscission. As the days shorten, the tree actively withdraws the valuable nutrients, nitrogen, phosphorus, and sugar from its leaves, pulling them back into the trunk and roots for storage. As the green chlorophyll degrades, the hidden colors of the leaf are finally revealed, the yellow xanthophylls and orange carotenoids, creating the fiery display of autumn. Once the nutrients are salvaged, the tree builds a corky scab at the base of the leaf stem, cutting off the connection and allowing the leaf to fall gently to the ground. The tree is now a skeleton, sealed tight against the cold, its metabolism slowed to a near halt. But for the conifers, the pines, spruces, and firs that keep their needles, the challenge is even greater. They must endure the freezing temperatures while remaining green. If the water inside their living cells were to freeze, the sharp ice crystals would puncture the delicate cell membranes, killing the tree from the inside out. To prevent this, the evergreen forest performs a feat of chemistry worthy of an industrial laboratory. As the temperature drops, the cells of the pine needles actively pump out water and replace it with concentrated sugars and special antifreeze proteins. This acts exactly like the antifreeze in a car radiator. By increasing the concentration of dissolved particles in the cell fluid, the freezing point of the liquid is lowered significantly. The water in the cells becomes a supercooled syrup that can remain liquid even at temperatures far below zero. In extreme cold, the liquid between the cells is allowed to freeze, forming a protective ice jacket, while the vital interior of the cell remains unfrozen and safe. This state of dormancy is a deep biological sleep. The sap stops flowing, the growth stops, and the tree stands in a state of suspended animation, waiting for the signal of the spring light to restart its engines. It is a masterclass in energy conservation, a refusal to fight the elements, choosing instead to withdraw and endure. We rest in the silence of the winter woods, surrounded by the sleeping giants, feeling the stillness of a world that has paused its breath. The transition from the sleep of winter to the final return to the earth is a move from dormancy to decomposition. The journey continues toward the art of decay, where we will see that in the forest, death is just another form of life. We acknowledge dormancy as the shield of patience, the quiet strategy that allows life to survive the dark times. We often view the death of a tree as a tragedy, a sudden end to a long life. But in the economy of the forest, a dead tree is perhaps more valuable than a living one. When a giant finally falls, brought down by wind or gravity, it does not leave the community, it merely changes its role. It becomes what ecologists call a nurse log. As the massive trunk lies on the forest floor, it begins a second life that can last even longer than its first. The bark, once a shield against invasion, now becomes a shelter. Moisture soaks into the wood, softening the rigid lignin that was forged centuries ago, creating a damp, sponge-like reservoir that holds water through the driest summers. This is the signal for the cleanup crew, the saprotrophic fungi and bacteria, the only organisms on Earth capable of unlocking the chemical vault of the wood. They release enzymes that chemically disassemble the cellulose and lignin, breaking the complex chains back down into simple sugars and raw minerals. This process releases heat, creating a warm microclimate inside the log that protects insects and salamanders from the winter freeze. But the most beautiful function of the nurse log is its role as a garden bed. The forest floor is often a difficult place for a tiny seed to start. It is crowded, dark, and covered in thick, stifling layers of dead leaves. The fallen log offers a raised platform, a VIP section where seeds can land and germinate in a bed of rich, rotting compost, elevated above the competition of the floor. If you walk through an old-growth forest, you will often see a straight line of young trees, hemlocks or spruces growing perfectly in a row. They are the children of the nurse log, their roots wrapping around the decaying body of the ancestor that is feeding them. Slowly, over decades, the log will completely dissolve, leaving the new trees standing on stilted roots, arching over a ghost. This is the art of decay. Nothing is lost, everything is borrowed. The calcium in the cell walls of the young sapling is the exact same calcium that once held up the giant for 1,000 years. It has simply been passed down. It is a perfect, closed loop of recycling where the waste of one generation becomes the food for the next. We rest in the presence of this slow disintegration, smelling the rich, earthy scent of humus, understanding that in the forest there is no waste, only transformation. The transition from this cycle of renewal to the final stillness is a move from the specific mechanics of life to the vastness of the biosphere. The journey continues toward the eternal breath, where we will pull back to see the forest as a single, breathing entity. We acknowledge the nurse log as the giver, the dead giant that feeds the living future. We have journeyed from the microscopic stomata of the first mosses to the towering canopy of the redwoods. We have traced the flow of water against gravity, the chemical warfare of the leaves, and the silent, underground trade of the fungal web. Now, as we stand at the end of this green path, we pull back to view the forest not as a collection of trees, but as a single, living organ of the planet. If you were to look at the Earth from space, watching a time lapse of the seasons, you would see the northern hemisphere turn green in the spring and brown in the winter. This is the visible heartbeat of the world, a slow, rhythmic pulse of carbon dioxide being inhaled and oxygen being exhaled. The forest is the lung of the biosphere, the great filter that cleans the sky and keeps the atmosphere in the delicate balance required for animal life. The physics of this place is the physics of patience. In the forest, time does not move in seconds or minutes. It moves in seasons and centuries. This is tree time, a temporal scale where a human lifetime is merely a brief, flickering moment, a single summer in the life of a grove. As you visualize this eternal wood, imagine yourself dissolving into the slow, heavy rhythm of the sap. Your breathing slows to match the respiration of the leaves. You are no longer a visitor passing through. You are part of the architecture, rooted in the soil, standing shoulder to shoulder with the sentinels. The anxiety of the fast-moving world fades away, replaced by the deep, resonant peace of things that grow. The green foundry continues its work in the silence. The fungal bridge pulses beneath your feet, and the archive of rings quietly records this moment of rest. We are surrounded by a life force that is ancient, indifferent, and incredibly enduring. The light filters down through the canopy in shafts of gold and green, illuminating dust motes that dance in the stillness. The wind dies down, the rustling of the leaves settles into a hush, and the forest waits. We rest in the knowledge that we are held by the earth, protected by the wood, and breathing the breath of the giants. The green is deep, the roots are strong, and the cycle is eternal. The boundaries of the self fade into the moss, the bark, and the air. The journey through the ancient life of the forests concludes here, in the heart of the quietest place on earth. The sunlight fades, the bird song stops, and we are left with the perfect, living silence of the trees.